Okay. Hi, everybody. Today we're going to be talking about the unit circle. This is a super important thing that you're going to use in trig, and it's important to understand it in a way where you're not just memorizing it, but really able to pick out any value from it just by understanding how it's set up. So first, we're just going to start with talking about a circle. So we know the equation for that is going to be x squared plus y squared is equal to r squared. And unit just means that the magnitude is equal to 1. So from here, I can rewrite my equation as x squared plus y squared is equal to 1. Pretty straightforward. And we're going to see that this specific equation works out really well with our trig functions. And you might remember one of our trigonometric identities matches up with this. So if I look at a point xy that is on this circle, I can find where my x value is. Am I going out? And I can find where my y value is by kind of going down and projecting onto the x-axis. And I can actually create a triangle that's going to go out to that point. And it's going to be a right triangle with angle theta. And so here, we know if we have a triangle with hypotenuse 1 and angle theta, then the adjacent side is going to be equal to cosine theta, and the opposite side is going to be equal to sine theta. So what that means here is that we're going to have cosine of theta is equal to x, because since we're starting here at the origin and the x-axis and going out, our angle is always going to be adjacent to the x-axis. Sine of theta is going to be y, because our y is opposite to our angle at all times. And this means tangent of theta we can write as y divided by x as long as x is not equal to 0. And we can also define our reciprocal function. So if I have secant of theta, I can define that as 1 over x. Granted that x is not equal to 0. Cosecant of theta is equal to 1 over y, where y is not equal to 0. And last but not least, cotangent of theta is equal to x over y when y is not equal to 0. So when we get into graphing all of these functions, you'll see all these functions with numbers in the denominator are going to have asymptotes when x or y equals 0. Another important thing about the unit circle is that it has direction. So I can move at a positive angle theta or a negative angle theta. So this example I showed you with my angle going up towards the positive y-axis or counterclockwise is positive theta. So counterclockwise, and I like to remember if we're starting at the origin and going up that we're going towards the positive y-axis. For a negative theta, so let's say we had negative theta going down here, we go clockwise. Or starting at the origin, we go towards the negative y-axis. So those directions are also going to matter. When we first start talking about the unit circle, we're going to look at just the positive angles, but over time, we'll be working with angles, rotations, and things like that. So since we know that 180 degrees is equal to pi, or that 360 degrees is equal to 2 pi, we can break our circle up into different angles just based on that. So I know I'm going to start at 0, and that 0 is going to end in 2 pi. That full circle is 2 pi, which means I can go to the opposite side and say that that's pi, right? Because 2 pi divided by 2. I can look at the positive y-axis and say, hey, that's going to be pi over 2, because it's 2 pi divided by 4. I can go to my negative y-axis and call this 3 pi over 2. And so on. And you can see that we're increasing in the positive direction. And so from here, and that's some other important angles. So I'm also going to add pi over 4, pi over 6, and pi over 3. And these three angles are just going to be extended into the other quadrants. So if I have pi over 3 here, I can rewrite it as 2 pi over 3 for the second quadrant, 3 pi over 4, 5 pi over 6. For the third quadrant, I'll have 7 pi over 6, 5 pi over 4, and 4 pi over 3. And then in the fourth quadrant, we'll have 5 pi over 3, 7 pi over 4, and 11 pi over 6. And the way we can actually get all these numbers simplified is if I start at 0 and go to pi. If I take this whole top half and divide it by 12, I start pi over 3 pi over 12, and so on. We can simplify it out to these angles. But the reason we're looking at pi over 6, pi over 4, and pi over 3 specifically is they correspond to our special right triangles that we've talked about earlier. So if I look at a 30, 60, 90 triangle, well, I can write 90 as pi over 2. I can write 60 as pi over 3. I can write 30 as pi over 6. And then for our 45, 45, 90, I can rewrite the angles as pi over 4, and then our right angle as pi over 2. So with the unit circle, you really want to get used to things being in radians. And I just always like to remember, well, I know my whole circle is 2 pi. I know half of it is pi. So any angle I want to find, I can use that relationship. So if I'm trying to remember what 90 degrees is, well, I know 180 degrees is pi, and I can just take half of that. So pi over 2 is equal to 90 degrees. From here, we can make triangles. So let's say I take this point right here at pi over 3, can make a triangle coming down with theta is equal to pi over 3. And I can find my x value and y value for that point by using sine of theta and cosine of theta. So if I rewrite this circle in terms of its x and y values, I can do that. And we see a really interesting trend. So if we look at just the x values to start with, I'll do those in red. So my x value at 0 is going to be 1. And that makes sense. We have this radius of 1. And it also makes sense with our values because x is going to be equal to cosine of theta, and cosine of 0 is equal to 1. So we start with 1. And then we'll go to pi over 6, or 30 degrees, and we'll get that we have root 3 over 2 for our first x value. Then we go over to pi over 4, and we have root 2 over 2. And then we go to pi over 3, and we have 1 over 2, which you could write as root 1 over 2, and it just simplifies to 1 over 2. And then at 90 degrees, cosine of 90 is equal to 0, but so we can write this as, 0 over 2, but we'll just simplify it to 0. So when we have x, notice that we're starting all the way at the edge of the circle, and we're kind of moving towards 0 on the x-axis as we go along this rotation. And this makes sense when we look at our numbers. We start at 1, the greatest possible value we can have, and we then have root 3 over 2, root 2 over 2, 1 over 2, and then 0. We're decreasing. And I'm going to have the opposite for sine, because for sine, when I start out at 0, I'm starting out on the x-axis at y equals 0. But then as I move up to 90, I'm going to be completely on the y-axis. So here, I'll start with 0, and then we'll have 1 over 2, root 2 over 2, root 3 over 2, and then we could write R1 as root 4 over 2. Simplify that to 2 over 2. That's going to equal 1. And so we kind of have the opposite pattern. So with sine of theta, as you go from 0 to 1, or 0 to pi over 2, sorry, you're going to increase from 0 to 1. Those are going to be the values you have. For cosine of theta, as we go from 0 to pi over 2, you're going to decrease. You're going to start at 1, and you're going to end at 0. And then everything else is just an extension of those coordinates that we have. So if I'm looking in my second quadrant, well, we're in the negative x-axis and the positive y-axis. So I can just rewrite this number up here as negative 1 over 2 and root 3 over 2. That'll still be positive. And I can extend it from there and have negative 2 over root 2 over 2, and then positive root 2 over 2 for the y coordinate, and so on. And then when I get to pi, I'll get negative 1, which makes sense. We're on the y-axis, or on the x-axis, my apologies. And then we're going to be at 0 for y. And then in our third quadrant, everything's going to be negative. And here I'm going to stop color coding just so I can write this a little bit faster. And here, well, everything is going to be negative. And you might be wondering how I know. I think it's tricky to remember where pi over 3 and pi over 6 go when we're looking at the other quadrants. But kind of just ask yourself, what is the distance from the x-axis? So if I'm over here, I'm looking at 30 degrees, it's going to be the closest one to the x-axis. If I'm on the other side and I'm looking at what is 5 pi over 6, that's also a multiple of 30. It's still the closest one to the x-axis. Sorry, this drawing isn't perfectly to scale. And so that's why here on the first quadrant, I have root 3 over 2, 1/2. And in the second quadrant, I have negative root 3 over 2, 1/2. So that's why when we're doing this, imagine we're going, if we look at our coordinates, if we look at just our red, our x coordinates. So I start at 1, I slowly go to 0. And then from 0, I'm slowly going to negative 1. So it wouldn't make sense to have root 3 over 2 right next to 0. It would make sense to have negative 1/2 next to 0. And so on. When we start at negative 1, I wouldn't have 1/2 after that. I would have negative root 3 over 2 and slowly go back down to 0. So that's a great logic check if you're ever stuck in trying to remember what your unit circle is supposed to look like, that the order has a system, that things are slowly increasing and decreasing as you're making your way around the circle because you're slowly moving up and down that x and y axis. And so that is a great way to check, like, okay, let me make sure this really makes sense. Okay. And then last but not least, we have the fourth quadrant where x is positive and y is negative. So I'll write that out for you. And these are going to be all of our values. So what's nice is you really only have to remember the first quadrant, right? You only have to remember from 0 to 90. And then everything else you can just extend. You can just remember the rules for each part. And an important thing I want to let you guys know is that there's a trend that you'll notice in your signs as you go through this. So in the first quadrant, all things are positive. Your sine is going to be positive and your cosine is going to be positive. So you have positive x and y coordinates, but you're also going to have a positive tangent because you have the like signs. In the second quadrant, only sine is going to be positive. So that makes sense because we have positive y values and negative x values. So if we have negative x values, cosine is going to be negative. And since we have different signs, tangent is also going to be negative. In the third quadrant, well, we have negative sine and negative cosine due to our negative x and y values, but because of those like signs, that mean tangent is going to be positive. And then lastly, in our fourth quadrant, cosine is going to be positive due to that positive x value. So that's another thing that you can use to kind of remind yourself, like, oh, well, if I'm looking at an angle in the second quadrant and I'm asked to find sine, cosine, and tangent for that, well, I know my sine has to be positive, my tangent and my cosine have to be negative. And this is also going to apply to your reciprocal functions. So if sine is positive in the second quadrant, so is cosecant. If tangent is positive in the third quadrant, so is cotangent, and so on. We want to remember that we have limits on our values. So sine of theta and cosine of theta, the smallest they can be is -1, and the largest they can be is 1. And this is just based on the rules of our unit circle. This has a radius of 1, so we can't get any bigger than that. From here, I'm going to take a break since this video is getting a little bit long. But then the next video, I'm going to talk a little bit about periodic functions and multiple rotations and how these functions are even and odd. But from here, I just really want you to remember that circle, we can find triangles in it. These triangles we can find specific angles in by breaking our circle into 360 degrees or 2 pi. And from there, we can find all of these coordinates in our circle. So I'll leave you guys there for now, and I'll see you in the next video. Thanks, and bye.